So good afternoon. I'm Tom Hickman. I'm the CEO of Tualatin Valley Water District, and we're here today to give a presentation on really what's our water distribution system, how's it work, and how do we get water from where we do to your home. So today we've got Pete Boone, who's going to be talking to you about that. Pete Boone has been with TVWD for 12 years. He started in 2008 as an engineer and has worked on a wide variety of infrastructure improvement projects over the years. In 2017, Pete transitioned to the Water Operations Division, where he leads our team of waterworks operators who perform all aspects of water system operations for the district. He's a registered professional civil engineer and land surveyor and holds degrees on forest engineering and civil engineering from Oregon State University. Outside of work, Pete enjoys outdoor activities like hiking, hunting, fishing, and foraging. He and his wife, Selena, live in Forest Grove, where Pete is also a volunteer firefighter and EMT for Forest Grove Fire and Rescue. So it is my pleasure to introduce Pete and the expertise he brings along with his team in making sure we deliver water reliably and safely to you every day. So with that, Pete, it's yours.
All right, thanks, Tom. And if someone could just confirm that they can see the slideshow on the screen as I kick this off, that would be helpful. So
I can, Pete. So
perfect. Okay. So as Tom mentioned, what we're going to talk about today is the anatomy and physiology of your water distribution system. And for anyone on the call who's got a medical background, you'll recognize those terms. And but don't be scared if you don't have a medical background. It's just it's a nice analogy to talk about how the water system works, because in a lot of ways it's similar to the human body, and the human body is a pretty amazing system, and we have a pretty amazing system here as well. So just a couple of reminders before we kick off. Please do mute your microphones when you called in to enjoy the show. If you do have questions throughout the presentation, please type those in the chat, and that's what this is all about. We want to interact with you, our customers. We want to be able to answer your questions and focus on the things that you're interested in. So put those in the chat. I will try to keep my presentation short so that we have plenty of time within the hour to address questions and have a good discussion about it. So first of all, let's talk about just the definitions of what we mean with anatomy and physiology. So anatomy is really just the structure of things. What are all the individual parts that we're talking about? And the physiology would be how those things interact with each other and what are the processes and functions of how it works as a system. So to talk about geography, to start with kind of where we are in the world here. So here's just a wide angle view of the northern Willamette Valley where we are located here. And TVWD, our service area, is the blue polygon there that's kind of in the center of the screen. To our west, we've got the Coast Range, and in the Coast Range, we've got the Joint Water Commission system, and that's there's a couple of raw water storage reservoirs in Barney Reservoir and Scoggins or Hag Lake. And those raw water systems feed into a water treatment plant that's near Forest Grove, and that's the JWC plant, the Joint Water Commission plant. And we bring that supply, they produce drinking water, we bring that supply into our system from the west at a couple of points along Cornelius Pass Road. We also get water from the Portland Water Bureau, and that water comes out of the Bull Run watershed. They also have the Columbia South Shore well field as a backup supply to that, and we bring that water into our system from the east. And you may have also heard about the Willamette Water Supply System, or WWSS. That's a big new supply system that's being designed and constructed right now that will serve not only Tualatin Valley Water District, but also the cities of Hillsborough and Beaverton. That's projected to come online in the year 2026, and that'll come up from the south. So that will draw water out of the Willamette River near Wilsonville, treat that water at a new plant that's going to be constructed near Sherwood, and then bring that on up to the partners that are in that system. And the city of Wilsonville and the city of Sherwood have been using supply from this same location on the Willamette for quite a few years now, since 2004. So that's been a proven good source of water. So if we zoom in a little bit and talk about our service area at a little closer view, we serve about 45 square miles. You can see where we're located here in between Beaverton and Hillsboro, bounded on the north by the West Hills, bounded on the south up onto Cooper Mountain, and then we also have our Metzger service area near Highway 99 and 217. We serve a population of a little over 250,000 people. We serve parts of some cities, so parts of the city of Beaverton, a little bit of the city of Hillsboro. We have service area agreements with both of those agencies, and we deliver that water through about 60,000 individual service connections. So the majority of those connections are residential. Our service area is a little bit interesting. It's unincorporated county. Most of it's developed in residential form, but it's the majority of our service area is not part of a city, and that's a little bit unique. A lot of times when you think of urban services, all of those are provided by a city government, but in our case, it's part of Washington County for the most part, and we are one of those service providers, along with clean water services for your sewer and stormwater treatment, and some others that round out that list of urban services. So here's another way to think about our system, and here's where we start to introduce topography with the geography discussion, and this is really important to how we move water around. So the blue line, if you will, goes from Cooper Mountain, runs north, follows roughly the alignment of Southwest 185th Avenue until it gets up to where it would cross Highway 26, and then that blue line turns and heads up towards the West Hills. So if you think about what that alignment looks like if you were to drive it, that's the lower part of your screen. So you would start up on Cooper Mountain at an elevation of about 800 feet. You would drive down to the valley floor, across the valley floor, and then back up into the West Hills. And so what's important about that is how it relates to water pressure. So if that from Cooper Mountain up to the West Hills were full of water, if we filled it up as a lake, that water would be about 600 feet deep. And at the bottom of that would be a very high pressure. So that would be problematic if all we had was tanks at the top of the mountain and pipes to serve all the way across the valley floor, because the pressure in those pipes would match closely this depth of water that would be if it were a lake. So if you lived on the valley floor and you had 260 pounds of pressure in your plumbing, every garden hose would be a pressure washer, and every shower would be a pretty painful event. So we regulate the water pressure, and we do that in a couple ways that I'll talk about here. But to tie this back to the human body and physiology, the corollary here that we would be concerned about is high blood pressure. If you go into the doctor, they check your blood pressure. If it's over a certain level, they're going to be concerned about that because it can cause problems in your own body, and they're going to try to regulate that as well. So the way that we do that is we divide our elevated zones in our entire service area into pressure zones and regulate that pressure, keep it down to a manageable amount, and that way we don't provide too much, but we always make sure we have enough. So as you go up Cooper Mountain, we've got a couple of pressure zones there that you can see, the same way across onto the West Hills, and we have more pressure zones than what's represented here just on the sketch, but gives you an idea of how we divide that up. Our supply and where it enters the system and the pressure that it is when we bring it in, you can see the advantage that we have by the pressure of the JWC supply, the pressure of the Portland supply come in higher than that water pressure that we need to serve to the valley floor. And that lets us serve a large portion of our service area just with gravity. We don't have to pump this water. We don't have to add any energy to it. We receive it at a high enough pressure that we can send that out to a large part of our customers. And this is what that looks like back on the map. So we bring that supply in. We can cover a good portion of our area just with gravity flow. So the different polygons on this map represent those different pressure zones. So, and the numbers correspond to the elevation that water would rise to if it wasn't confined into the pipes. So gives you a sense of how we can move water around. If you look at the south part of that, up onto that Cooper Mountain area, we've got a pretty good collection of pressure zones. So that's because that elevation is changing quite a bit. Same in the West Hills. You can almost follow the bands of elevation with those pressure zones. So we've got our service area divided up. Okay, so we bring water in from Portland and the JWC. We can serve a lot of that just under the gravity, the pressure that we receive it at. But to get it up to the upper elevations, we have to pump it. So we do that with electricity. We've got 13 different pump stations. Most of those stations have multiple pumps inside of them. And if we do lose that electricity, they've all got backup power generators. So we can turn those on when PGE loses power, and we can continue to pump water as we need to. And not surprisingly, the analogy here with the physiology is our own heart. Of course, our bodies only have one, and when it fails, that's a pretty big problem. So we like the redundancy of having the multiple pump stations, multiple ways to move water around. The other thing we do with water is we store it. So our storage reservoirs are, not surprisingly, a lot of times located in the elevated zones. A lot of pressure zones have multiple reservoirs for redundancy. Some pressure zones don't have their own reservoir at all, but they sit below one. So they take advantage of that storage that it is at a higher elevation. Our tanks range in size. We've got 23 of them. They range in size from fairly small, so 125,000 gallons, all the way up to 10 million gallons. So our largest tanks are 10 million gallons. And this gives us a total, if they're all full at the same time, it's 67 million gallons of storage. But bigger is not always better, and especially when it comes to water storage, because a really important part of our mission here is serving high quality water, and we want that water to be fresh. And so if you can imagine, if you have very large tanks and you're not able to circulate the water through those very easily, you got a big volume of water that's going to be getting older all the time. And so we spend a lot of time making sure that we can move that water through our system, bring it in as supply, deliver it to our customers in a short amount of time, so that it's nice and fresh when we do that. And if you think about the scale of 67 million gallons, it's somewhat comparable to the Moda Center. So if anyone's been to a sporting event or a concert out there, some rough math gives you an interior volume if the Moda Center was full of about 200 million gallons. So we've got a little bit less than that in storage, but we're also, always bringing in more and sending it out through our service connections. It's interesting to think about going to a sporting event or a concert in the days of COVID and how long it's been since we've done things like that. And of course, a big component of our water system is our pipe network. So we've got to move this water around. We do that through the pipes, and it takes quite a network to do it. So we've got over 750 miles of water main, and those range in size from 54 inches in diameter all the way down to 2 inches. So as you can probably imagine, the bigger pipes are tied to the reservoirs in most cases, and you can see that on the map. And then we step down as we get into the neighborhoods with smaller pipes, similar to the blood vessels, going from arteries to capillaries and such. So most of the neighborhood pipes, a distribution pipe on your street, will typically be a 6 or an 8-inch diameter. And then the service line from that pipe to your home is going to be a 3/4 or a 1-inch diameter. And how we size those pipes, especially the distribution lines, is by fire flow. So if we did not have to deliver fire flow to hydrants, most of our distribution pipes would be smaller diameter, because domestic flows are less than what a fire department's going to require if they're battling a fire. So our pipes are sized to deliver those larger flows, and make sure that we can always provide water to those hydrants in an emergency. And of course, our own human circulatory system is a good proxy for how we move water around as well. All right, so let's talk about some of the brains behind the system. So beyond our operators who bring their brains to work and make critical decisions all the time about this stuff, we have a computer network that's connected to most of the facilities in our system. It's a network of sensors that are constantly monitoring what's going on out there, and it helps us to keep track of what's going on. It also provides quite a bit of automation to the water system. So we call this SCADA. That's an acronym for Supervisory Control and Data Acquisition. You'll find SCADA networks in all kinds of applications, from industrial manufacturing to other utilities and things like that. So this screen here is one of the, it's just an example of what an operator would see when they're interacting with the system. So there's a graphical representation of what's going on. This shows a pump station with all the different pumps. It shows the reservoirs that are upstream of that are being pumped into. And SCADA is what's monitoring the water level in those tanks. You got some pressure information here, some flow rate information, water quality, all kinds of things. And of course, the central nervous system in the body is performing those same functions in people. So if you think about a heart monitor, if you've ever had to go to the hospital, or maybe you've just seen it on TV, this is helping doctors and paramedics monitor what's going on in the human body, showing you trend lines, showing you what's going on, and how things are changing. And that would allow those medical folks to make interventions, make decisions about what they might need to do or how the body's reacting. And really, that's what SCADA is doing for us. So here's a screen showing some parameters in the water system as they change over time, and we're able to process that information and make decisions. So to recap, on the anatomy portion, we talked about supply, how we bring water into the system, how we move it around, we pump it, we store it. We've got our system divided into pressure zones. One critical thing to mention about that storage is, that's what helps us not only be prepared for emergencies if we were to lose one of our water supplies, but it also really helps to regulate that pressure. So as demand changes, and I'll talk about demand in a little bit, as that changes, that water in the tank is always there to provide more supply as needed. We got the pipe network and of course the SCADA system. All right, so let's transition to the operational strategy, or the physiology of the system. And again, if you have questions as we're going through this, type those in the chat and we'll have some time here at the end to address those. So what we're looking to do when we operate the water system, number one, we want to manage our supplies. We want to make sure that we're bringing in enough water to meet our customer demands. And when we talk about customer demands, that's the amount of water that folks are receiving from our system, how many taps are on at the same time, and how much water is leaving our distribution system. We obviously want to do that under an adequate pressure. Nobody likes to have their water pressure be too low, so we're balancing that with the way that our system is designed. And we're keeping that water high quality. So it has to have a chlorine residual for a disinfectant. The addition of chlorine to drinking water was one of the major public health improvements that occurred in the early 1900s in helping us to prevent waterborne diseases. We talked about water age, wanting to serve that water when it's fresh, and then the aesthetics of it. So the customer experience, you want your water to be clean, visibly. You don't want to see a color. You don't want to have a funny taste or odor to that water. So we certainly want to manage all those things, and then make sure you always have access to this water by minimizing service disruptions. We want our customers to always be able to turn on the tap, not have to think about whether or not it's going to be working. So a little more on water age and water demand. So this time of year in the winter, we are serving, and it's a very steady amount, at about 16 million gallons per day. So it goes up and down a little bit, but there's not hardly any irrigating going on right now. So the demands are very steady day to day. That changes in the summertime as there is more irrigation and other uses of water, and we'll see that daily demand go up into the 30 and 40 MGD range when the weather changes. And that's really what drives it. It's weather, it's temperature, precipitation, and how much folks are watering. Those are the big drivers in the fluctuations that we see in water demand. So when demand decreases, when we're serving less water out of our system, the water age tends to go up. So the time that it takes water from the day that it comes through one of our supply points to the day that it goes out through someone's tap, that's how we measure water age, and that can tend to increase when we're in periods of lower demand like we are now. And one of those challenges is the chlorine residual tends to decrease as the water gets older. So we want to maintain that residual. We do not rechlorinate the water that's out in the system. So the best thing we can do is manage the system in a way that just uses up that water. And that storage can be a challenge. We talked about it earlier. So if we have large tanks, if we're not able to fluctuate those and use the water out of them before we refill them with fresh water, that can add to our water age. So one of the ways that we do that and manage water age, especially in our tanks, is with a concept of respiration. So when you think about how your bodies respirate, you breathe air in, you breathe it out. We try to do that same action with the water level in our tanks. So on this SCADA screenshot, the blue line that you see at the bottom, that's measuring that water depth in the tank, and we're just trying to cycle that up and down. The top blue line that you see on that screen is a measure of that chlorine residual that's in the water, and you can see how it responds to that respiration. So as the tank level rises, it's fresh water coming in, it's got a higher dose of chlorine in it, and that maintains that nice residual that we have in there for to maintain water quality. All right, so a little bit about how our system reacts and changes to fluctuating demand and things like that. In our human bodies, if we're under exertion, our bodies compensate. They react to that by delivering more oxygen to our tissues. We do that by increasing our heart rate. Your breathing rate goes up, and similar things happen in the water system. So if demand goes up, customers are using more water, maybe there's a fire flow. The water level in the tank is there to serve that need, but it might draw the tank level down as it does so. When that happens, when the tank level drops, our SCADA system can detect that, and if it needs to turn on an additional pump to send more water up to that tank, it'll do so. And at the same time, our operators can monitor that what's going on, and if they need to change supply or make other adjustments, they're able to do so. And we think about that in terms of automation. So the reaction that SCADA does on its own based on the programming that's in there, or intervention when an operator would make different changes based on other information that they're seeing. A couple things that we do to make sure that we have high quality water, and you might see us out in your neighborhood doing this. So we flush. That does a couple benefits. So one, it'll remove sediments that are naturally occurring in the water. So our water coming in from surface water supplies, especially the Bull Run, can have some naturally occurring sediment. Most times it's undetectable, but over time, as it settles out in the pipes, it can leave a natural deposit layer, and we want to flush that out. So you'll see us in your neighborhood doing this. You might see the water coming out with a little bit of brown color as that sediment gets mobilized, but it is still safe to drink. We also do this to manage the water age. If the water is getting a little bit older, we don't have kidneys or livers like our human body does to refresh that. And so again, we try to use it up, and if we can't, then sometimes we will flush it out. We're continually monitoring the system, so we take samples, send those off to the lab. We have online instruments that monitor different water quality parameters throughout the system, but all focused on making sure that we have high water quality throughout the distribution system. And unfortunately, sometimes we do experience service disruptions. So those can come in a couple different varieties. So some are planned, some are due to maintenance or construction on the system, and we have to shut down parts of our distribution system, turn off your water for a brief period of time, make some changes, and turn it back on. Other times that can happen under an emergency situation. If we have a main break, if we have to do an emergency repair, and in those instances, a lot of times we're not able to let you know ahead of time so that you can plan as our customer. But we try to minimize that impact by having multiple ways to deliver water. So having a strong network, a pipe network to move water around helps with that. And really how you can help us help you is if we have current contact information for you. So if we have a phone number that we can call you, if we have an email address, we can reach out to you. That's really helpful for keeping you informed as our customers. So you can update that contact information by going to our website. If you're watching this presentation later on YouTube, we'll have that information in the description. So you can click on a link to contact us and update that information, or you can always call us and our customer service staff will help you through that. A little bit about main breaks. So our 750 miles of pipe, unfortunately, sometimes they do leak and they do break. So we'll respond and fix those. Actually, we had a crew this morning already that had to go out and fix a leak. But luckily, we were able to do that without disrupting anyone's service on that street. The majority of our pipes are made out of either ductile iron or cast iron. Those two, they're both metals, obviously, but they both react a little bit differently to changes in the underground environment. So this time of year, the soil moisture is changing as we get more rain. The temperature is dropping, and both of those things can combine to cause some shifting soils, and that can put stresses on the pipe. It can crack the cast iron because it's a little bit brittle, and the ductile iron is a little bit different. It's not as susceptible to the shifting ground conditions, but it is somewhat susceptible to corrosion, and so that can eat holes in the pipe that eventually cause a leak. These two graphs just show kind of the times of year when we see a lot of leaks, and we're in that time of year right now. So December and January tend to be our peak times. That's largely driven by the shifting soils that I mentioned and an increase in shear breaks, which is what we call the cracks in the cast iron. The corrosion, that can really affect us any time of the year. It's fairly steady. Those are the blue bars on that graph. And this is 5 years of data, so it shows over that period of time kind of what we've experienced in the system. If you look at it year by year, we usually experience somewhere around 60 main breaks annually. We're a little bit less than that now, but we are still in December. We expect to have a few more. I used this presentation about 3 weeks ago, and the 2020 number for main breaks was only, I think, 27 at that time. So it is always changing. And these numbers are a really important point to remember about this. As pipes begin to experience corrosion, especially, once they start to leak, they will continue to leak unless we replace them. And we do have a program here to replace those mains once we discover that they're starting to have more corrosion issues. And without replacing those mains, you would see these numbers go up considerably. So we are constantly making improvements to the system and trying to minimize these service disruptions. And SEISMIC. So if you've lived in the Northwest for any period of time, you've certainly heard about the Cascadia subduction zone earthquake. So this is an event that has happened here before. We expect it to happen again. And when it does, it has the potential to cause significant damage. So we've made significant investments over the years. We continue to do that. And that's, again, all aimed at having a resilient system that can survive and recover when we do experience this earthquake. That photograph is from Alaska, from a recent earthquake. And you can imagine if there was a water pipe buried in that roadway, it would not have survived that type of ground motion. We will have a huge advantage when the Willamette system comes online from the resiliency standpoint. That system is being designed and constructed to withstand the Cascadia subduction zone event. So that'll be a big advantage to our customers when we get that online. And the graph here just reflects some of the investment that has been made over the past 30 years here at the district. So a lot of our reservoirs have been either replaced or upgraded with strengthening and other measures to allow them to survive an earthquake, and if there is any damage, to make sure that that's minor and that those facilities are still functioning. And lastly, I talked a lot about anatomy. I talked a lot about physiology of the system, but a really key part of it is our staff. So the folks that operate the system, that is a 24/7 job. I mean, the water system is always working. It's always available for you, and sometimes, actually fairly often, that requires these folks to work outside of the normal 9 to 5 hours. So if you have a main break on your street in the middle of the night, odds are you're gonna see us out there fairly quickly. We might be making some noise while we deal with that, but that's all to keep your water service intact and make sure that it's available for you. So we appreciate these folks. We hope you do too. And we would be happy to answer any questions that you have about any of this stuff. And also let us know if certain parts of this you want to take a deeper dive into it. We can do future discussions like this on other topics.
Thank you, Pete. Also, thank you, Tom, for kicking it off. And we apologize. There's been quite a number of technical challenges with this this particular event. We're trying to support quite a few customers on email, trying to get them onto the system as well today. So we're suspecting that Microsoft Teams did an update, and so nothing is where it was in our previous events. But we have some great questions coming in, and we're going to field those with our subject matter experts that are on the call. And we do appreciate your participation in these forums, both on your behalf to learn, but also on our behalf. We learn a lot based on the questions that you offer. So we're going to kick it off with the Q&A session with a question that came in from Cliff. He lives on Cooper Mountain, and sometimes, several times a day, he has a lower water pressure, and he wants to know if there's any reason for that.
All right, so yeah, Cliff, great question. And I will begin by guessing that you live on the upper elevations of Cooper Mountain. And if that's correct, then what you're probably experiencing is changes in the pumping up there. So if you think about the very top of the hill, we have a water tank that sits at the top of the hill, but we don't have a water tank that sits high enough above the top of the hill to provide that tank pressure back to those customers. So we directly pump to that part of the distribution system. So when we turn pumps on and off, we always have one running because that's what maintains that pressure to the upper part of the Cooper Mountain. But if demand increases and we need to turn on additional pumps, when that second pump kicks on, you might see an increase in pressure, and then again when it turns off, that pressure may drop. So that is probably what you're experiencing. Cliff, if that's not the case, if you're further down on the mountain, and you can certainly follow up with us and check in with your address, I could give you a more detailed answer.
Okay, thank you, Pete. And the next question that we have in is going to be from a person who dialed in. What do you spec the water pressure for individual homes? I've seen my water pressure vary from 50 PSI to 150 PSI, even with a pressure regulator installed at my house.
Okay, so couple of key thresholds on pressure here. So we shoot for a minimum pressure of 40 to 50 PSI to our customers. Now there's a few parts of the district where that's a challenge to provide that much, but if we're less than that, it's usually in the high 30s. As a public water system, we're required to provide at least 20 PSI. And if any part of our system is over 80 PSI, the plumbing code, which governs the individual plumbing in your home, requires that you have that individual pressure regulator. So there are parts of our system that provide over 80 PSI, and that's when you'd have those regulators. It's really important to recognize that those regulators can fail. They are a mechanical device, and sometimes they need to be replaced, and sometimes when they do fail, they will allow a much higher pressure to come into your home. So that may be part of what you're seeing there. But it is important that you keep track of those devices, make sure they are working properly, because if that high pressure does come into your plumbing and it wasn't designed to withstand it, you could have other issues.
Okay, the next question is, are the pipes earthquake ready? What is the plan in the event of a large-scale event, such as an earthquake, to keep water flowing to our homes and fire hydrants?
So great question. We have some pipes in our system that are considered resilient. We've made a lot of improvements recently as we've learned more about that expected level of shaking and what it might do to the underground pipes. But not every one of our 750 miles of pipe is considered earthquake ready. So there may be damage to those pipes. Certainly if we got the big one today, we would expect quite a few main breaks, and that would impact our ability to deliver service directly to your homes like we do today. So in response to that, we would have to go out, isolate those leaks, turn off parts of the system that were leaking so that we could keep the rest of it intact, and then be making those repairs as part of our recovery. In the future, we have plans to upgrade a lot of our piping, put in what we call a resilient backbone, a network of strengthened pipes that would survive an earthquake. But if things were really bad, and we were not able to use large portions of our system, we have other ways to provide water. We are a water provider. That's our mission. We like to do it using the distribution system when it works, but if it really had a widespread failure, we can set up water distribution stations where you would have to come to us and fill a container. But we have ways to provide water out of our storage reservoirs. That's a big reason why we've invested so heavily in strengthening those reservoirs. So yeah, it's something we think about a lot. We've got long range plans to continue to make improvements to our system, but it is going to take us a while to get there.
If I could add to that, Pete, this is Tom Hickman. One of the biggest investments we're making right now is on the Willamette River water supply, and that project meets all the seismic standards for a pretty significant seismic event and gives us additional redundancy in our supply. That project isn't going to be done until 2026, but it is critical as part of the backbone to be able to continue to provide water after a significant seismic event and supply it to the region. So that's one of the big investments we're making. The other thing I would encourage you to do is I'd have to ask Andrea here, but I believe I know we've had prior sessions like this discussing earthquake resiliency, emergency resiliency, and what to do. So I believe those are still posted on our website, Andrea. And
yeah, that's correct. And we will post the link there underneath that question here as soon as we can. Maybe Frank, you can chime in real quick and tell me what the short link is.
Yep, I will go ahead and post it.
Okay, great.
Perfect.
And our next question, but we did hold, as Tom mentioned, we did hold 2 other forums this fall on emergency prep, and it does get into a more extensive explanation about what you should expect and how you can prepare your home now in order to be able to sustain your own household until we could get water service restored to you. So the next question up was from Gabe. Thank you very much for submitting your questions. Do you plan to read meters remotely? And we have a number of subject matter experts on the call, but I don't know who's best positioned to tackle this. It might be you, Tom, but if it's someone else on our staff, just jump in there.
Sure. We do one part of the area of the Tualatin Valley Water District service area. We do have automated meter read systems in place. They're called drive-by. So essentially, a meter reader drives by and usually can pick up the signal and read the meter that way. However, that's a relatively small portion of our customer base. We have had a number of internal discussions. We have done an initial look at bringing to the district what we call AMI, which is Automated Meter Information Systems. So those can be read essentially remotely. They don't even need to have a drive-by. We are looking at possibly putting this as a budget suggestion to our board and to see if there's a desire to fund that. It will take a number of years to implement. It doesn't happen overnight, but it is something that we're very interested in, want to do, and we believe ultimately we need to do because there's a number of reasons and there's a number of benefits, not just to our customers, but also to us in terms of more accurate real-time information to get that kind of stuff. So I would encourage you to keep watching and stay tuned, and we'll see where we end up here at this next budget cycle, and it might end up being the budget cycle after that before we could afford to implement that. There's a significant upfront cost, but there's a lot of big benefits once you make that investment.
Okay, great. Thank you. So we do have a couple questions now. We're going to introduce a new subject matter expert. We're going to have Joel Carey. He's our Water Resources Division Manager, tackle these next couple, and they're related to fluoridation. So we have one question, are you adding fluoride? And one is, what's the purpose of adding fluoride to our water systems? Maybe you can tackle those together, Joel.
Yeah, thanks, Andrea. Good afternoon, everybody. Yeah, so the purpose of adding fluoride, obviously, I should actually take a step back in time so folks understand that the district's been fluoridating since 1963. That is something that was enacted by the customers, i.e. voters, during that time period and has remained that way since then. So I think that answers at least part of the question as to why the district currently fluoridates. And kind of the broader question as to why, well, obviously there's a lot of information from both the CDC, the U.S. Department of Health and Human Services. Those are some of the public health bodies that we reference when we talk about the requirements that our customers asked us to do for fluoridation. So, the underlying principle of fluoridation is obviously to promote dental health. And I want to stress too that the district does it in a manner that meets the latest criteria, both in terms of how we do it, the products we use, and the levels that we administer, which is 0.7 milligrams per liter. So there's a lot of information posted on our website if you're curious about that. And additionally, you might hear a lot of us say this when we answer these questions too, but if you have more specific questions when it comes to these types of concerns, feel free to shoot us an email or call us too, and we'll happily walk through you in as much detail as possible. So I hope that generally answers the question. Yes, we add fluoride, and the purpose is really for the promotion of dental health based on our customers voting it in.
Andrew,
I think you're muted.
But now I know where it is. So yeah, this next question's from Gabe. How exposed is this system to droughts?
So I'll jump in, and Joel, this is Pete again, and Joel can back me up. So anyway, drought could be a concern in the Northwest. We've experienced drought in the past, but we got a couple things working in our favor to help us mitigate that. The biggest one is our variety, our portfolio of water supplies. So we're members of the Joint Water Commission. So that supply is located in the foothills of the Coast Range. Obviously, the Portland system up on the flanks of Mount Hood and their well fields gives us some diversity there. And then when the Willamette system comes online, we'll have yet another watershed that we're able to access and help guard against that. We also have wells in our system that are available to us, and we use those in a manner called aquifer storage and recovery, ASR, and that's where we actually can inject water into these wells when we have an abundance of supply, and then it's available. It's stored in the basalt aquifer, and it's available to us in times of peak supply or drought, to where we could pump that back out. So yes, we think about drought. We do try to have ways of mitigating against that, and we are in a pretty good position as far as water systems go, and having those multiple sources of supply.
If you don't mind, I'll just add to that what Pete just said too, which is all exactly correct, all right. And a good example of that is one of the years we had not that long ago was 2015, when we had a fairly substantial drought declaration across the state of Oregon. But if you may recall, if you were a customer of ours during that time, we didn't require any voluntary or mandatory curtailment for our customers. And it's largely what Pete pointed out too, is just the resiliency of our supplies. So it's important to remember, when you see that stuff in the news, that there's a lot of planning that goes into the type of work we do for our supplies, and the two aren't necessarily directly linked in the same way. There's a lot more nuance behind it than that. So, and it's not that we don't, we pay attention to that. There's a lot of effort and planning that goes into that. We're well aware of conservation. We practice and promote that. But yeah, there's quite a bit of additional resiliency that we've built in behind that. And then I want to make one other clarification too, just to point out for folks. Regarding the fluoride question, reference our website, as I mentioned, because there are areas of TVWD that are not fluoridated. Metzger portion is not the larger area, the 2/3 of it, what we sometimes refer to as the Wolf Creek, but that is fluoridated based on that vote. So a nuance to that question, please see our website or shoot us an email if it's not clear enough.
Okay, thanks, Joel, and I'm glad you're getting warmed up because we do have a series of questions that are going to come to you as the primary person, and others may jump in. But Janet wants to know if we are adding more chlorine recently. When she gets a glass of water, she can smell the chlorine, but it does quickly dissipate. And there's another person who's signing on to that saying they can smell it very strongly at their house.
Yeah, so I can tackle both those more or less. And much like a lot of our answers and responses, you know, there's a whole multitude of things that we could talk about. We could probably spend another 20 minutes on that one alone. But, you know, chlorine, the short answer to that is the district, for the most part, doesn't add any additional chlorination to our system once it comes in from our sources. Pete referenced our thing called ASR, our groundwater sites. We do a little bit of supplemental or post chlorination at those sites, if you will. But in general, the answer is no. Oftentimes, really, it comes down to the fact that chlorine is a reactive type of chemical. It's there for an incredibly important reason for public health protection. But over time, it will dissipate. Typically, when it's in your home, it's dissipating as it runs through the piping, the system, and reacting with your internal plumbing. By the time it gets to your faucet, that's oftentimes when you notice that smell, that taste, that odor from chlorine. It's doing its job. We measure it 24/7, 365 days a year throughout our system at multiple key locations. So we see that almost near real-time data. All our operators see it all the time around the clock. So we're well aware of what's happening with the chlorination in our system. But it doesn't mean you can't experience that. We've got some helpful tips that we could provide, simple things you can do as well, just to help dissipate that. You might notice it more often in the morning when you first get up. That's always one of the telltale signs. As chlorine is, again, sort of dissipating as it runs through the plumbing in your house and before it comes out of your faucet. So nothing to be alarmed about. But again, you know, our staff are here, and if you shoot us an email or give us a call, I mean, we'll even give you exact levels that we see out in the system as we collect samples throughout the distribution system each and every week as well.
Okay, great. Thanks, Joel. And then we do have a question here. I think this one might be for Pete, but do you have a 1-year representation of the water main breaks? And generally, have breaks gone up or down over the past year?
Sure. So I will actually go back to a slide that shows that exact thing. So the graph to the right, main breaks by year. So that's for the past 5 years, how many total each of those years we've experienced. So you can see they do fluctuate. We've had years that are higher than this. We've been over 100 in some years, and that's where I mentioned the investments in mains replacement. You know, finding those pipes that we have that have failed, frankly, and making the decision to, rather than keep repairing them every time they break and making a disruption in the street and all that. Let's just put in a brand new pipe. Let's stop having these problems and prevent those future main breaks on that same pipe. So we are constantly working on that. And I look at this graph and I see these numbers and they actually make me very happy. So we are in much better shape than a lot of water systems around the U.S. If you look back east on some of the systems that have been in place for much longer than ours. Just the age of those pipes and the different materials, you know, cast iron that's 150 years old in the city of Boston or New York is those systems are going to experience a much higher level of breaks. And you know, we express that in terms of, you know, breaks per 100 miles of pipe to kind of to normalize the data. But we're in really good shape when you look at those metrics compared to other systems. And like I said, we're always making improvements and trying our best to minimize these disruptions.
Okay, so just to clarify, Pete, that blue graph, the one on the far right, that's the breaks so far this year?
Yeah, so each of the past 5 years, and then 2020, the bar on the right. So actually this data is old now too. I mentioned we had a break this morning, so we've responded to 37 now instead of 36.
So we still have until through the 31st to make that firm up, right?
Yeah, place your bets. How high will we get?
Okay, yeah, see, we could have a little side thing going here. Okay, then the next question is, do you have a groundwater supply other than the Portland well field?
So I'll start on that, and Joel can jump in as well. Yes, we do. We have the Grabhorn ASR well that's located in the southern part of our system, right around the base of Cooper Mountain. We use that every year. We inject water into that basalt aquifer there. We store that and then turn around, and in the spring we pump that back out. So folks in that part of the service area, you are getting some water that has lived in the ground. It's not necessarily groundwater itself, but we do utilize that investment, and we have a couple other emergency wells available to us also.
Nothing to add. Perfect.
Okay, Gary also submitted a question. With the computerized system in place, how do you protect yourself and us, the customer, from a virus or intentional act to disrupt our water delivery system?
Yeah, great question, Gary. Yeah, certainly in the age of more and more cyber attacks and risks related to that, is something that we have to be very careful with. So our SCADA system is highly secure. One of the ways that we ensure that is it's not connected to any other networks or the internet. So we keep that very well firewalled off and isolated. We're always monitoring the security of that, and we're very confident in the measures we have in place. And like I said earlier, so SCADA networks are very common throughout the world and run all kinds of systems, including the power grid and different systems that are all need to be very highly secure. So you know, we've got physical security, we've got security technology built into it. It's a very robust and secure environment.
Okay, and another question from Gary. When will the Willamette water supply be connected to our area?
So the Willamette is scheduled to come online in 2026. So what we would anticipate is that would be brought on and be serving water before the summer of 2026. That's when we see our demands go up. So we want to have that system available to us in what is that, 5 years from now, 5.5.
Okay, and another question that we have is, let's see here. Sorry about this. Getting new questions coming in, so there is still a chance to ask your question. Sorry, it keeps bouncing.
So I can see a couple of these, Andrea. It looks like.
Okay. Did you present a similar talk on water chemistry, including finishing and disinfection? That was a suggestion from John. And we will be scheduling our topics. We'll resume these forums after the holiday season in January. We do approximately one a month, and all the participants will receive a survey from us at the end today, and you'll have an opportunity to let us know other topics in addition to this one. We'll add this to the list, John, that you'd like to hear a similar kind of format talk about your water system. And then another question we have in is, how can I protect my 20-plus-year-old pipes in my home from breakage from water pressure?
So if you're concerned about that, if you'd like to reduce the water pressure to your home, you can do that with a pressure regulator. So that's a little mechanical device that gets installed on that line your water line as it comes into your home. If you're handy, you can do those yourself. If you'd rather have a professional do that, that's always a good idea to get a plumber involved. But that's a device that you could control and dial down the pressure where it enters your home if that's something that you're worried about.
Okay, and we do have another question about detecting leaks. How do we detect leaks, and at what time do you decide that the pipe needs to be replaced?
So we detect leaks, and actually I have a slide for this as well, so I will jump back. So a big main break, if you will, so one that's going to put a lot of water on the surface, a lot of those get reported to us by folks that are out in the community. So when you see a bunch of water bubbling up out of the road, if it looks like it's coming up under pressure, odds are that's a main break. Give us a call. We'll come out and take a look, and if we need to respond and repair it, we will. That response and repair can be an interesting operation. Trying to figure out whether or not it's a main break can be a challenge. So lots of things can put water to the surface, and they're not always coming from our pipes. So we do investigate those and make sure that we can figure out what it is. It could be coming from an irrigation system or a private plumbing system. You know, there's a lot of investigative measures that we have available to us. We can test the water. We can see if it has chlorine, if it has fluoride, some of these other constituents that would tell us whether or not it came out of our system. And one of the most effective things we can do, if we want to think about medical analogies again, is listening. So our form of a stethoscope can be in the form of a metal valve key, like you see in the photo here, but listening to hydrants, listening to valves, putting your ear up to those things. A lot of times you'll be able to hear that a little bit of a hissing sound from the pressurized water if it is coming out through a leak, especially a smaller one that's harder to detect. Now, when we look at a pipe and try to figure out if it's failed or not, a lot of times, you know, that has to do with the condition of it. Looking at whatever damage had been caused to it, whether it's from corrosion or some other means, and trying to determine if it's, you know, worthy of repair or if it really ought to be replaced. And a lot of time that's a judgment call. We've got engineers on staff that help us with those decisions, and we've got a matrix that we work through, and a lot of it has to do with leak history. If we start to see a pattern on a certain section of pipe, that's going to push it close to the top of our list to get replaced. So hopefully that answered.
Yes, it did. We just did have one other question come in. It's from Cliff. In regards to the low water pressure on Cooper Mountain, the low pressure has only been over the last few weeks. So it sounds like a new condition.
Okay, and I did see on there that Cliff said he was on Gassner Road. So how about this? Cliff, I'd like to talk with you directly so I can get some more information about that, and I can certainly help track that down. So if you can maybe coordinate with Andrea, you can call in and we'll get in touch with you and see what we can find out. Oh, you got muted again, Andrea.
Okay, Cliff, if you just put in the Q&A how we can reach out to you, so you don't have to share it with everyone on the call, then we will follow up and get in touch with you, either a phone number or an email, whatever your preferred way is. And so this is pretty much a wrap. We're a little bit over time. We want to thank everyone for participating. And if you do have individual concerns, you can always reach us at the office at 503-848-3000. And we do really enjoy these events, and we hope you're enjoying them as well. An opportunity for us to interact and teach you as well as learn from you. So again, we just want to thank you for participating with us today.